All right, good morning, everybody. See, I have my COVID hair. That's my son. First lecture. We're starting in chapter 1, the properties of gases. Here's the game plan. We'll talk about ideal gases, hopefully familiar to you. We'll talk about the kinetic theory of gases, which relates molecular behavior to these things that we can measure.
Gases.
And then we'll talk about real gases, specifically the van der Waals and virial equations. One question you may be asking is, why are we studying gases at all? And I think there are two reasons. So the first is sort of historical. Gases are the medium in which the laws of thermodynamics were developed. The second is related, and it turns out that gases are really the simplest systems that we can envision, and they give us a reasonable handhold to start to implement some of these formulas and ideas from thermodynamics. Solids, liquids, proteins, any condensed phase thing is a lot more complicated. And so gases give us a good starting point. Okay. Oh man, this drives me crazy. Good, I figured it out, how to advance my slides. If you're watching, pause for a second and do this. I'd like you to draw a gas and answer these questions. What are the characteristics of the gas and what properties describe it? I'll give you a minute, hit pause, and I'll check back in with you in a second. All right, hopefully you're done. First question I asked you to do is to describe the characteristics of a gas, and hopefully you drew something that looks like this. I'm gonna switch my pointer. So we recognize that gases are made up of atoms or molecules which are in constant random motion. Gases are going to fill the space that's available to them. And what is sort of unique about gases compared to liquids is that they're widely separated. Right? They're a long ways apart from one another. We commonly make two simplifying assumptions, or at least there's a starting point for making these. And that is that there are no intermolecular forces. The only way these molecules interact are through so-called hard sphere collisions. They bang off one another. The second is that because they're so far apart, we can basically totally neglect the size of the molecules themselves. It's inconsequential. If we make these two simplifying assumptions, we get what's known as an ideal gas. And we will go back to this idea throughout the whole semester. So good thing to start with. All right, what properties describe a gas? These should all be things that you may know and love, or that you could guess from the ideal gas law. So the first would simply be the number of molecules or moles of stuff that are there. The second is the volume that this gas is taking up. Third one is the pressure. And when you think about pressure, what you should really be thinking about is a measure of how hard these molecules are whacking the walls, right? Last but not least is temperature. And when you think about temperature in the context of the gas, what you're really probably imagining is how fast the molecules are moving. You have an intuitive sense that when the gas heats up, molecules go faster. And that's exactly right, but that is a little different. These properties that we're describing here are all macroscopic properties, or something you could measure. And how fast a molecule is moving is a little bit different thing. If you actually look in Atkins, what you'll see is that he defines temperature a little bit different. It's defined as the property that indicates direction of energy flow through a diathermic barrier. That basically means if I have two things at different temperatures and I put them in contact with one another, I can tell you which way energy will flow, right? We'll talk about this throughout the semester. It's not critical to know right now, but just be aware that we're here talking about macroscopic properties of these systems. Some more definitions. So all of these variables from above are what are called state variables. State variables only depend on the current system, not on its past history. Right? So if I tell you the temperature of the system, its temperature is whatever it is. I don't need to know what it was, a week ago. All of these state variables are interdependent, and one of the goals that we're going to try and do here is to find an equation which specifies all of these state variables. If I do that, I will have fully described the system. And because that system is fully described, one of the ideas is that I have two systems which are in the same state. They're indistinguishable. There's another definition that you'll need to know and that I'll talk about throughout the semester. I'm going to switch my pointer again here. I'm going to write in blue. So Atkins doesn't use this language, but it's worth keeping in mind. The idea here is what I call extensive and intensive variables. Extensive variables are one whose magnitude is proportional to the amount of stuff that's present. Right? More stuff, the variable gets bigger. There's a classic example here, and that's, say, volume. Twice as much stuff will take up twice as much space. On the other hand, intensive variables are one whose magnitude is independent of the amount of stuff that's present. An example that you might think of here. If I could get my pen to write, that would say temperature, but there we go. Temperature, right? Twice as much stuff at 100 degrees Celsius is the same as twice as much stuff at 100 degrees Celsius. It doesn't matter. One trick that we'll commonly use in thermodynamics is to create intensive variables from extensive variables. And the way that we do that is dividing them. So if I take two extensive variables and I divide them by one another, you can get a extensive or an intensive variable. And so here's an example. If I took volume and I divided it by the number of moles, right, which is also an extensive variable, you get what's called the molar volume. So many liters per mole, for instance. And we'll use this trick throughout the semester to convert between extensive and intensive variables. All right. A couple more comments here about these variables. So the first is regarding pressure. Recall from your physics that pressure is force per unit area. The SI unit of pressure is the Pascal, formerly 1 Newton per meter squared. And one of the things that you're going to have to get used to with pressure units is converting between them. So common pressure units are the atmosphere, torr, Pascal, bar, PSI. And I listed some common conversions here, but you're going to want to make sure that you can do units conversions and you're fluent with all of these things. Second one is the volume. What you may or may not remember is that the SI unit of volume is the cubic meter. Right? We don't use the cubic meter a lot in chemistry. We use the liter. And so you're going to, again, have to be able to convert between these common units, liters, cubic centimeters, whatever, and the SI units. And again, there'll be some practice problems where you'll get to do all this stuff. Last but not least, temperature. Note that all temperatures are measured on an absolute scale, Kelvin. And so you'll want to remember that you've got to convert things to Kelvin temperatures in order to get lots of these equations to work. All right, I mentioned that one of our goals was to interrelate the state variables. And if we do that, we get something called an equation of state. So the goal here is to predict a mathematical relationship between the gas state variables based on this picture that we have. And this has really some historical development through what's known as the gas laws. You probably learned about these in your introductory chemistry course. There are 3 or 4 of them. I'm going to quickly run through them. The first is Avogadro's principle. It basically says that volume is proportional to the number of moles, right? Really simple idea. More stuff takes up more space. Second one is Charles's law. Charles's law relates volume and temperature, or you can also modify it to relate pressure and temperature. And what this basically says is that as I heat a system up, a gas up, the molecules move faster and the volume increases. Same thing with pressure. If I heat it up, the molecules whack the walls harder. So we find that volume is proportional to temperature and pressure is proportional to temperature. Last but not least, we have Boyle's law. Boyle's law relates pressure and volume. And what Boyle found out was that if I multiply those two variables, pressure times volume, you get a constant. The idea here is that if I decrease the volume by a factor of 2, you have twice as many collisions. And those two factors offset one another. So pressure times volume is a constant. I can take all of these gas laws and I can summarize them into one version, the ideal gas law. So if you're recording some notes and this is not familiar to you, you'll definitely want to put this in your notes and become intimately familiar with it. But the ideal gas law says PV equals nRT. Pressure is volume, pressure is P, V is volume, N is the number of moles, and T is the temperature. Last but not least is this guy R, and R is the ideal gas constant. Oh, our cat just walked in here. Thanks, buddy. I hope that you've seen this before and that you've used it. There's some example problems where I will ask you to do some simple calculations, but recall that R comes in many different versions. The two most common ones are here. Pointer options. All right, so this is going to be a really common one that we use, the SI version of R, 8.314 joules per k mole. The other one that is really common is this one. Recall that 1 cubic decimeter is a liter, right? So R is also 0.08206 liter per atmosphere mole K. All right, I'm going to stop here. There are some simple example problems for you to work through, and I will see you at the next topic. All right, bye. If I can figure out how to stop recording this.